Okay, okay, so this is going to be 9.2, which is called the dot product. So still talking about vectors. But before I get into 9.2, I want to uh, give a quick recap of a certain type of problem in 9.1 because I think it's really, really important. So I want to look at decomposing a vector into into horizontal and vertical components. This technique in vertical components is going to be like the bread and butter of any physics problems or engineering or applied math kind of, well, physics being the main one, I suppose. One of the bread and butter techniques that you have in your physics classes if you have to take physics. So decomposing a vector into horizontal and vertical components means to take some vector that is given with some magnitude. So we'll denote that with the vertical bars there, some magnitude. So this is a vector v with some magnitude of that, and then at some angle to the horizontal line here of theta, right? So maybe we're given that a rock is thrown with a speed of 10 meters per second in the at an angle of, let me say that, at an angle of 30 degrees to the horizontal. To the horizontal meaning like 30 degrees from the horizontal line, like from the ground or something like that. Find its speed in each direction, in the vertical and horizontal direction. So why would you want to know this? Well, you can tell a lot of things once you learn to decompose these vectors, once you get a little bit of physics under your belt. Vertical and horizontal direction, right. One thing that is very straightforward that I could just teach you right now is that if you ignore air resistance, if you're throwing a rock and it's going, this like following a parabola, right, parabolic motion here, if you ignore air resistance, which is what you do in your first level physics courses, then the horizontal velocity, or horizontal speed, I'll say, of the rock is never going to be slowed down. It's never going to change, right? It's never going to speed up because the rock doesn't have like a rocket attached to the back of it, so it's never going to speed up, and it's never going to slow down horizontally because there's nothing pushing back on it. Now its vertical speed is going to change because of gravity, right? Gravity pushes straight down, so its vertical speed will be changing. It'll be at a maximum right here, and then it'll slow down and reach zero at the very top, right? Its vertical speed will be zero. It'll stop moving up and down for a moment, it'll be suspended, and then it starts to speed up and come back down. So there's lots and lots of things you can say about this sort of projectile motion problem, but the very first thing you need to know how to do before you can get anywhere is how to decompose this vector. And we know that we have, how does the book denote it? Well, I'll just denote it like this because this is how you'll see it in your physics courses. The x component of my vector v is going to be equal to the magnitude of v, so these are the same v's, times cosine of theta. And that's just from trig, right? It's like saying cosine of theta is equal to adjacent over hypotenuse, where this adjacent side is the Vx that I'm looking for. That's the horizontal component, right? So like if this is magnitude of v there, that's like the hypotenuse, and then this is vx, and this will be vy, and then there's theta. So this should seem familiar just with different numbers happening here, different letters rather. And then v sub y will be the magnitude of v times sine of theta. And there we go. So there are the horizontal and vertical components to this vector in general. And now what I've done is I've given the vector a magnitude of 10 meters per second. That's this magnitude of the vector. And its direction is 30 degrees. So now I can plug some stuff in. So I can say that the speed in the vertical direction, with v sub y, is equal to the magnitude 10, right, the magnitude times sine of 30 degrees. And then vx will be equal to 10, so this is the horizontal direction, 10 times cosine of 30 degrees. Oops, forgot my degree symbol. There we go. So sine and cosine of 30 degrees, well, recall, that's a 30, 60, 90, like this. There's my 30-degree angle there. And draw my little reference triangle. It's going to look like this. So sine of 30 degrees is just going to be 1/2, right? Opposite over hypotenuse. So v sub y is just going to be 10 times 1/2. In other words, 5. Okay, 5. And v sub x is going to be 10 times adjacent over hypotenuse, well, square root of 3 over 2. So that'll give me 5 square roots of 3 when everything is said and done there. Okay. And at what angle would these two vector components be exactly the same? Because they're not the same here, right? It's faster in the x direction. At what angle would they be exactly the same? Well, right down the middle, right at a 45, if it was a 45-degree angle, right down the middle, then these would be exactly the same. But since it's a little bit lower than that, it has a little bit more speed in the x direction than it does in the y direction. Okay. And now, like I said, there's lots of interesting questions we can ask from here using physics tools, right? But for just vector math, this is as far as we want to go in this course. Okay. So now let's actually get into 9.2, which is called the dot product. So you've seen in the videos excuse me. You've seen in the videos that I've posted that you can add vectors. We've learned how to add and subtract vectors, both by component and so by component and graphically. Right, we've done that. And you've also seen how you can multiply constants onto vectors, which when we say a constant, like just a number, right, we need to now differentiate between a number and a vector, right, because there's a lot of different types of numbers floating around. You can multiply by scalars, which is just a real number, right, not a vector. Multiply by scalars, and we learned how to do that by component and graphically. So we've seen that. Good. So what happens when you multiply, or what's going on for multiplying by vectors, vector times a vector? And that's what this section is going to start to answer. So let me just tell you right off the bat that there's more than one way to multiply two vectors. There's more than one way. And the two most common ones, the two main ones, are the dot product and the cross product. And they both have just so many meanings in physics and engineering and applied math, like the dot product and the cross product. If you are doing any kind of modeling, any kind of thing where you're modeling with just all sorts of things, you're gonna need to know what a dot product is and a cross product is, especially if you're going into calculus. Well, I should say, if you're going into calculus, you'll be expected to do more modeling problems, so dot product and cross product are going to be useful to you there. We're just going to talk about the dot product. Okay. So first of all, what is the dot product? Let me go ahead and give you the definition of the dot product here. Let's let U be some vector with components, so I'll denote it like U with a little line above it to denote vector U, and then inside of here these are just going to be numbers U1 and U2. There we go. And then vector V will be V1, V2, so just naming its components after its vector name. So these are just numbers in here. Then the dot product, U dot V. So we don't say like U multiplied by V or U times V. We literally say U dot V, or the dot product of U and V, because the cross product notation, which is a different kind of multiplication, looks like this, and it means something. It's totally different from the dot product. In fact, we'll see that this is just going to give a number, and this gives a whole new vector. A special vector, but anyways, we're not doing that here, but I just want you to know whenever you say, when you're describing this product, you're going to describe it as a dot product, like literally a dot. Okay, what it is, it's the product of the first two components of each of the vectors, U1 times V1, and that's just regular old real number multiplication, because remember, these are just numbers, right? And then plus that same product, but for the second components. There. That's it. That's a dot product. That's a dot product. So it's very easy to calculate. You can do it in your head, right? Let's do an example. Now, I told you it has significance in applications. It has great significance graphically too, so we're going to talk about that, but first let's just practice using this definition. Let vector U equal 3, -2, and vector V equal 4, 5. Find U dot V. So find U dot V, the dot product of U and V. Okay. So I could write them in component form and put a dot between them. That's okay. You can do that. In fact, that might be helpful just to be able to make sure I'm getting the calculation right. So I should have 3 times 4, the product of the first two things, plus the product of the second term, so -2, or the second components, -2 times 5, and that's going to be 12 minus 10, which is 2. So something to note is that it yields a number, not a new vector. Okay, it yields a number. It yields a, well, in the jargon of chapter 9, it yields a scalar, not a vector. See, this is just a scalar. It does not pop out a vector. It takes in two vectors. And pops out a number. Okay, I'm going to call this part A. Do part B now. Part B, let U, vector U, equal 2i plus j, so giving it an ij form here, and V equal 5i minus 6j. And recall that this is just another way to write a vector, just using those unit vectors. I and j are unit vectors. So here we have vector, well, let me say it like this. Vector u is 2, 1, 2, 1, and then we're going to have dotted with 5, negative 6. So remember, that's how the ij form works. These each represent, the coefficients here of I and j are representing the components inside the vector. So what's happening is, just so you know, so we're clear about this, I is a unit vector in the x direction. Unit vector meaning it has length 1. Okay, and j is the unit vector in the y direction. And if you're in 3 dimensions, then you can have k, you know, being the unit vector in the z direction. If I did that, I would need another little, another component, right, to go to 3 dimensions, and that's perfectly fine too, but we're just talking about 2 dimensions here. So, like for vector v, for instance, this literally means 5 times the vector I, which is that, and then minus 6 times the vector j, and then we know how scalar multiplication works, right? You send the scalar in, so this is 5, 0, and then minus, send this scalar in, 0, plus 0, negative 6, because I'm sending the negative 6 in, so I'll write a plus there, put the negative in there. And then just add these vectors by component, right? 5 plus 0 is 5, and 0 plus negative 6 is negative 6. Long story short, this is what happens, right? You don't need to do all this every time, right? The idea is that you don't do this every time. You understand that the coefficients of I and j are the components. Okay, so now let's get back to computing this dot product here, this particular dot product. So I'm going to take the 2 times 5. I'm just going to skip a step here. 2 times 5 is 10, and then I'll say minus 6. That's a 6. 1 times negative 6, and that's giving me, I'm going to do it here, 4. There we go. It's that easy. Computing a dot product, you should be able to do it in your head once you know how it works. And depending on how bad the components are, right? If the components are fractions or whatever, then maybe want to write it down then. Okay. Let's just talk about some properties of the dot product real quick. Anytime you introduce a new operation in math, you should talk about its properties, like how does it work with other kinds of operations, is it commutative or just all sorts of things like that. So let's answer some of those questions. First of all, it is commutative, meaning you can swap the order. So u dotted with vector v is equal to vector v dotted with vector u. It's commutative, meaning you can swap the order, it doesn't matter. And why is that? Well, if we look at the definition of the dot product, it's just multiplication and addition with real numbers, right? With just numbers. And multiplication and addition is commutative. So I can reorder this all I want, which would in effect reorder this, right? I can reorder this in the right way, swapping the correct things so that the v and the u end up swapping around. No problem, right? No problem. So the commutativity here I would describe as being inherited from commutativity of addition and multiplication for real numbers. All right, part 2 here is, what is that? Some scalar c times vector u, so that's just a number times a vector, and then dotted with another vector is the same as that scalar being on the outside, and also the same as the scalar multiplying onto the other vector. Essentially, this actually tells us a lot. It tells us 2 things at once, which is that well, what does it tell us? It tells us you can reorder, let me say it this way, you can reorder the scalar and the dot product basically in any order you want. You can stick the scalar wherever you want. You can stick the scalar on the first vector and then take the dot product, or you can take the dot product and then then get the scalar involved, or you can take the scalar on the other vector and then do the dot product. It doesn't matter. That scalar can commute wherever it wants to. So that is what that is telling us. Okay, we have the distribution property dotted with, oh, this should be, I'm trying to follow along in the notation they give in the text. So there we go. That's u plus v dotted with w is equal to u dotted with w plus v dotted with w. In other words, distribution holds. Kind of like normal multiplication, right? There's a distribution property. And finally, the magnitude of a vector squared is equal to itself, its dot product with itself. Its dot product with itself. So the magnitude of a vector squared is equal to its dot product with itself. Okay, now that we have these properties, let's see. So we want to get to the graphical representation of the dot product, like what it means on the graph. So let's talk about that. So if we have two vectors, u and v, dotted together, we can describe this as the magnitude of u times the magnitude of v, so that would be a normal multiplication there, not a dot product, because magnitude of u is a number, magnitude of v is a number, so this is just like a normal multiplication, right? And then, well, inside there's still vectors, I should say, like that. There we go. But the output of this magnitude would be a number, and the output of this magnitude would be a number. And then times cosine of theta. Okay, so this is the dot product over here. Where theta is the angle between the vectors. Between the vectors u and v. So this may not seem like, I said this is the graphical representation of the dot product, but what does it really mean? Well, what is, how do we get a picture involved? Well, I think it'll make a little bit more sense if I reorder this formula so that cosine of theta is isolated over here, and I say is equal to u dotted with v, vector u dotted with vector v, over the product of their magnitudes. And what does this mean? What does this mean for us? This means if we know, what do we need to know to compute dot product? The components, right? That's what we need to be able to compute the dot product of the vectors then we can find the angle between them. And that is a very, very useful thing to know how to do in physics and engineering. So let's run an example. Example 2, let's find the angle. Let's find the angle between vector u, which, so you do need the components. You do need the components to be able to find, because you got to know the dot product. And the dot product requires that you know the components. So 4, -3. Okay. Find the angle between these two vectors. Okay, so I'm going to say cosine of theta is equal to u dot v, so maybe I'll just plug in u and v up there. So 2, 5 dotted with 4, -3 over the magnitude of, you could do all of this on the side. You don't have to plug it in like I am. Magnitude of 4, -3. So in the top, I'm going to have 2 times 4, which is 8, plus 5 times -3, which is -15. So in the top, I'm going to have 8 minus 15. What about in the bottom? Remember how magnitude works. It's the these are like the sides of a right triangle, right? And you want to find the hypotenuse. So thinking Pythagorean theorem, then the magnitude, here, let me just write the formula down over here. Where am I going to write it? How about down here? So the magnitude of some vector u1, u2 with components u1, u2 is equal to the square root of u1 squared plus u2 squared. So just the sum of the squares of the components under a square root. Pythagorean theorem, that's all it is. Acting like these are the sides of a right triangle. Okay. So I'm going to have square root of 4 plus 25. Probably wrap that in parentheses, that's the first one. And then times 4 squared is 16, and then plus -3 squared is 9, so plus 9. All right, so I've got some algebra to do here. First of all, in the top, that's easy, -7. In the bottom, I'm going to have square root of 29, and then times square root of 25, just adding 4 plus 25, and then 16 plus 9. Okay, and then I'm going to have -7 on top, and then square root of 25 is 5, which I'll write on the left side now since it turned into a whole number, and then square root of 29. Okay, great. That's not an angle, though, right? So where am I? So I'm at cosine of theta is equal to -7 over 5 square root of 29. And you may say, well, this formula doesn't give me theta explicitly, but it does give you cosine of theta, so we know how to find theta now. We take the inverse cosine on both sides, which will effectively cancel this cosine function out, or cosine expression, whatever you want to call it. Cancels this operation out on the left side. So theta will be equal to cosine inverse of -7, this whole ugly fraction thing. So we go over to the calculator. They didn't specify to find it in degrees or radians. I'll just find it in degrees. So let me put my calculator in degree mode. I'll say cosine inverse of -7 divided by, probably need to wrap this in parentheses so the calculator knows that the entire thing, 3 parentheses, right? Yeah, there we go. All right, and I'm getting, the angle between these is, I'll say, approximately 105.1 degrees, if I round. Okay. That's one of the useful things about the dot product, is that it shows you through its calculation with the magnitude of each of the vectors there as well, the angle between the two vectors. Let's graph them and see if it looks right. So let's graph these two vectors. Oops. Okay, vector u is at 2, 5, so that's roughly up here somewhere, 2, 5, 2, 5, and vector v is at 4, -3, so I'll go over to 4 and go down 3, somewhere down here. So does that angle look like 105 degrees, the angle between them? I'd say yeah, it's pretty close to it. It's definitely bigger than 90. All right, that looks about right, 105 degrees. Okay. Here's a cool fact. Two non-zero vectors are called perpendicular or orthogonal if the angle between them is 90 degrees, or pi on 2. Orthogonal, by the way, is just a fancier way to say perpendicular in 2 dimensions, basically. Okay, all right. And here's a fact. So this is just definition, right? Which this is what you would guess it would mean anyways. This is what perpendicular means for lines, so why would it mean anything different for vectors, right? U and V are perpendicular if and only if, meaning it's necessary and sufficient for the dot product to be what? What would it be? Well, if the angle between them is 90 degrees, we have this formula that says cosine of theta should be equal to dot product over magnitudes, right? If the angle here is 90 degrees, what does this actually output? So there's stuff up here, stuff down here, but what is cosine of 90 degrees? Well, it's 0. Okay, so what does that mean about the numerator up here? It must be 0. But what is the numerator? It was the dot product, right, in the formula, u dot v. And then down here, it doesn't say anything about the magnitudes. But if the angle between two vectors is 90 degrees, then the dot product between them must be 0. And it holds in the opposite direction too. If the dot product between two vectors is 0, then the two vectors are perpendicular, or orthogonal, if you'd like that, if you like that better. Okay. That's a very, very useful fact. So example 3 says, determine whether the vectors are perpendicular. This idea about the dot product being 0 if and only if the angle between them is 90 degrees is used in a lot of proofs that you'll see in calculus. It's a very heavily used fact. Determine whether the vectors are perpendicular. So part A. Now, just looking at them, you can't really tell, right? Looking at their components, you could tell maybe a little bit better if you graphed them, but the fastest way is to just go straight to that dot product and say u dotted with v will be equal to 3 times 2, which is 6, plus 4 times negative 8, which is negative 40. That's not 0, so they're not perpendicular. I don't even need to finish calculating it. If all the question is asking is, are they perpendicular? That's all I need to do. See if it's 0 or not. Part B is two new vectors, 2, 1, and v is -1, 2. This seems like it might have a better chance, but we should calculate it to be sure. U dotted with V is going to be equal to 2 times -1, that's -2, and then plus 1 times 2, which is 2, that's 0. They are perpendicular. Nice. Really fast way to tell if two vectors are perpendicular. Now the rest of the section gets into projections and things, components of vectors along other vectors, and then some applications from physics. But this is as far as I want to go in with vectors. So this is the last bit of material for the whole, well, it's actually not. This is all we're going to do in chapter 9. I still need to show you guys what the law of sines and law of cosines are, because you may remember that we postponed those just because of time. But now we have time at the end of the semester, so now I'm going to go back and do those. But as far as how much further we're going to go into the textbook, this is it. But now we're going to go back to section 5.5 and 5.6, which was the law of sines and law of cosines. Okay, but this is it for 9.2.